The pleasure to introduce today Iyad Rahwan as a keynote speaker at Alive. He's a director of the Max Planck Institute for Human Development in Berlin, where he founded and directs the Center for Human and Machines. He's also an honorary professor at the Technical University of Berlin and former associate professor at the MIT. His research looks at the interplay between autonomous systems and society, asking questions about how these systems should interact together, the relations of ethics and AI, and whether we can program moral principles in autonomous systems. And Iyad has contributed to projects like the Moral Machine, about experimental ethics for autonomous vehicles, or automation, innovation, and the future of work. And so many of his projects are motivated by the question of how can science help us understand, anticipate, shape, and major disruptions from artificial intelligence, the web, or social media in our societies. So, you can ask questions during the talk using the Q&A panel and also the Slack channel. And so many thanks, Iyad, for being here, and please go ahead.
Thank you so much, Miguel, for the introduction. Thank you also to the ALAB community for hosting me. It's very exciting to speak to this audience because I think they are a very important part of the research agenda that I will outline today. So today I will talk about machine behavior, this notion of machine behavior, and maybe different aspects of machine behavior. So the talk will be split into three parts. First, I will outline what we mean by the idea of machine behavior. And then I will give you two different lines of research that I've been involved in around machine behavior. One has to do with human-machine cooperation. And the second one has to do with cooperating through machines. And I'll explain how these things relate to the behavioral perspective on machines shortly. So first, let's talk about the research agenda on machine behavior, which I think, the ALAV community has already been doing this, obviously, for a very long time. So it's not something that I've invented. It's just something that has crystallized in terms of communities of scientists coming together and saying, this is really a thing that is very interdisciplinary, and it should become even bigger than these individual research communities working on it. So the question, first of all, is what is computer science? I think that's a very fundamental question. So we could think of computer science as mathematics. You could think of somebody like Dijkstra as just a mathematician. He famously didn't have a computer for most of his life. I think they convinced him at the very end. And for him, doing computer science was something you do with pencil and paper. So computer science is the study of algorithms, theoretical study of algorithms. You could also say computer science is engineering. So a good example of a computer scientist as an engineer is Grace Hopper, who was credited, I don't know how accurate this is, but often credited for finding the first actual computer bug in a computer. And for somebody like Grace Hopper, doing computer science means, building something, and then if it doesn't work, then you have to go and fix it. You have to find kind of engineering solutions to it. So it's like building bridges. And then the third is computer science as science. And this is really a big, difficult question. Like, what does it mean to have computer science as science? And I think one way of thinking about it is to think of the notion of machine behavior. Excuse me, I'm staying in a hotel, actually, which is why there's some sounds in the background. So we wrote together with scientists from a whole variety of fields, computer science, political science, robotics, psychology, anthropology, and so on. We wrote this review that was published a couple of years ago, titled Machine Behavior, where we tried to outline the fundamental questions of the science of machine behavior, which is a scientific hypothesis-driven approach to studying machines, to complement this engineering perspective and the mathematical perspective. So if you think about it, it's important for computer ethics or AI ethics, because you often cannot certify that a machine is ethical by looking at its source code and doing some kind of theorem proving. Not so much, not more than you could do the same with a human. You know, with humans, we were able to regulate human behavior and to predict human behavior for, you know, we're very good at predicting the behavior of other humans, right? And so that we can establish who to trust and who to do business with and who to mate with and so on, without understanding the brain, because we have a good folk theory of the behavior of humans. And now the question is, you know, so if we can develop a good theory of the behavior of machines, then we may be able to regulate many machines, even if we don't have access to their complex inner workings. So think of the following questions. You know, these are questions about news ranking algorithms or algorithmic justice. Is an algorithm, does it discriminate? Does it do something, you know, does it create filter bubbles and so on? You could study these things mathematically, or you could study them using other methods, right? Like using behavioral methods that, for example, economists or psychologists might use. Same thing with autonomous vehicles. Questions about, you know, is a car driving aggressively, or how does it distribute risk between passengers and pedestrians? These are behavioral questions fundamentally, which again, you could study from an engineering perspective, or you could study completely observationally. Same thing with markets, you know, if we look like the emergence of collusion or manipulation in markets, online dating and its impact, as well as the impact of conversational robots on children, for example. Again, you could in theory study a lot of these questions, let's say as a psychologist or as a political scientist or economist, without knowing computer science. And if you can't, then why not, right? Like the question is, we're trying to reduce the barriers to enable all behavioral scientists, not just computer scientists, to study machines. So in a way, what we're calling for is a kind of behavioral revolution in the study of machines. So we have to go back to the behavioral revolution in psychology, and people like B.F. Skinner and others who, you know, took like a model, like let's say an animal model, like a mouse, and you could think of like an algorithm as like a mouse. And you could, of course, study its morphology, for example, you know, what does it look like? Just like you could study the source code of a machine, or you could study it using the experimental method by putting it in a maze or putting it in a box, something like a Skinner box, and you change some kind of stimulus and you measure some kind of behavior, right? So you could do something similar with machines without understanding or looking into the inner workings of the machine. And if we do this, we could develop benchmarks that then we could then hold different machines too, right? So we don't care how your algorithm is implemented, but we have developed behavioral tests for establishing whether they are good enough at something. And this is something the machine learning community obviously is already doing. You know, they're developing all these computer games, tournaments, and classification tasks. You know, benchmark classification tasks are examples of this. But I think we need to take this much further. You know, we need to take it into the realm of behavioral study of everything that any behavior that machines can exhibit. It's kind of an old idea if you think about it, because the work of Herb Simon, who was incidentally won the best prizes in economics, computer science, and psychology, wrote this book, which not many people know, in the 60s, called The Sciences of the Artificial. And in this book, he contrasted natural science, which is explored knowledge about the natural objects and phenomena like trees, the weather, and animal behavior, with artificial science, which is knowledge about artificial objects and phenomena, things like machines and institutions. And of course, you can't study the individual machine behavior alone. You have to study the collective behavior, which is something that the alive community has worked a lot on, but also the hybrid emergent behavior that arises from the interaction of humans and machines collectively. So how does this relate to other fields? I see it as something that intersects between the engineering of artificial intelligence and the study of the scientific study of behavior. And I think you can easily recognize then that the alive community is very much in this space already, right? And has been for a long time. And I see it as distinct from the study, like fields that study the impact of technology, for example, in law, in ethics, kind of normative disciplines and then humanities, things like science and technology studies that use qualitative methods. What they do is they provide new scientific questions that then can be explored through machine behavior, and they can also incorporate new quantitative evidence from the science of machine behavior in order to generate engineering practices. How do you, for example, for value-aligned design. And the last part of the paper on machine behavior took inspiration from the founders of the field of animal behavior, these three gentlemen who won the Nobel Prize for the founding of the field of animal behavior, and specifically for the work of Nicolas Tinbergen, who's very famous for the 4 fundamental questions in biology, or what have become the 4 fundamental questions in all of behavioral science. And these questions, so these are not our original invention, but we've adapted them to the study of machines. So you could distinguish the different types of questions you can ask about behavior from a dynamic perspective or a static perspective, and you could look at the proximate view or the ultimate evolutionary view. So for example, you could look at a proximate view, which is how a particular type of machine functions, and you look at only a static explanation of its current behavior. So you look at the causation, you try to understand the cause of a particular behavior. Okay, when I give the machine learning algorithm this particular input, adversarial input, then it misfires. Or you could look at, how did this develop? What data went into training this algorithm, or what experiences did a reinforcement learning algorithm have that generated this kind of behavior? You can also ask, what is the adaptive value of the behavior? Is it making money? Is it maladaptive? And are the incentives aligned with the behavior that we expect, or is the institutional setting creating kind of perverse incentives? And ultimately, I think there is a kind of evolutionary process taking place on algorithms. Obviously, it's different from biological evolution. And I think this is a very interesting area of exploration for the iLife community, because obviously a lot of work in artificial life tries to explain and understand mechanisms of organic life. But there are things that computers can do that are completely different. For example, you could copy instantly across, like let's say an autonomous vehicle can discover a new behavior that is adaptive, and then you could push it basically like an app update on like 1 million cars all at once, right? So it's a bit maybe closer to something like cultural evolution in human behavior. Okay, so that was the research agenda on machine behavior. But then we could also distinguish the questions of machine behavior into 2 types of questions. So we could ask questions about the behavior of the machine itself. That's everything I've spoken about so far. Or we could also, and I think this is another important question, is we could explore facts about how humans perceive and expect machines to behave. And that's a question about human psychology more than machine behavior, but it's obviously the two interact. So I'm going to give you some examples of the first and then some examples of the second type of question. So let's think about the behavior of machines. For example, autonomous vehicle. Should the autonomous vehicle crash into a number of pedestrians, or should it swerve and kill a person on the side, or should it hit a wall and kill the person in the car? You could ask this question. You could ask, what does a particular car do, right? How is it programmed? What does it actually do? Is it learning different behaviors over time? Or you could ask people, what do they think the car should do, right? So that's a question about human expectations. Or who do they blame when something wrong happens? That's an equally important question. Here's another question about perception. So when people use AI for art, to generate art, who do people allocate? So first you can ask, is this art original? What is the nature of this creative behavior? Or you could ask, as we did in this paper, who do people attribute credit for? Or if there's a copyright violation, who do people think should be blamed? Is it the programmer? Is it the person who used the tool? Or is it the AI itself in a way? And so on. So recently we wrote a paper together with Jean-François Bonnafont about also how people's folk theories or theory of mind affects their perception of machine behavior. So this is more like a perspective piece to try and set a research agenda. So you can think of an AI system, you can think of a perspective of a developer and of a user. And users can think of, okay, this machine thinking intuitively, or is it thinking analytically? And that's something that Daniel Kahneman, for example, and others have popularized a lot in recent years. And you could ask, many different questions, like from an engineering perspective. An engineer could ask to program a particular kind of fast behavior or slow behavior, right? So heuristic behavior or rule-based behavior. Or even a UX designer may even program the machine to appear to be thoughtful. So even though the machine can compute the answer very quickly, it can slow down the answer to give the impression that it's thinking deeply, right? So, and these, of course, there are ethical concerns and questions that arise here. And from a user perspective is both a user experience perspective, do they prefer machines that are more slow or fast, and for which tasks? And do they require, legal thinkers and ethicists require a particular kind of thinking? Okay, so now I want to, let's move to like specific projects. The first project has to do with cooperating with machines. And here's, the background to this is that we have, as you know, a lot of benchmark problems in human-machine interaction have been zero-sum competitive games, right? So chess and poker and Go and all of these things, one party wins, the other party loses. And there's a particular kind of, obviously it's exciting because it's about competition between humans and machines, but it also has a particular structure that allows certain kind of analytical or heuristics to work well. There is obviously work on cooperative robotics, but these robots are typically subservient. So it's more like a tool or a slave to the human. It's programmed to behave cooperatively. Well, if it's programmed well, successfully. But I was more interested in this kind of question, this image here. So there is a machine, and the machine doesn't belong to the human. It belongs maybe to somebody else. But if the machine finds itself in a situation where it might benefit from cooperating with the human. But if the human is not cooperating, perhaps not, right? And there's a really interesting question here about the interplay between this, between human behavior and the way that these computers are programmed to play these kind of games. So this is the well-known prisoner's dilemma. I'm sure you know it, but let me just very quick abstraction of it. That's what we use in our experiments. You have like a blue and a red person here, and each has a square, but the square is valued more by the other person. So the red person values the blue square twice as much, and the blue person values the red square twice as much. So the best thing to do is to exchange those squares, and everybody ends up with twice as much. Now, obviously, there is an incentive to keep what you want, what you have, right? So for example, the red person here doesn't give the square away and ends up with more. And there's, of course, symmetrically, the incentive is the same for the red person. So in equilibrium, this is the dominant strategy equilibrium from game theory, everybody keeps what they have. Now, if you play this game repeatedly with some kind of expectation of future cooperation, then cooperation can emerge. And there are literally thousands and thousands of papers in mathematical biology and in computer science as well, of like reinforcement learning algorithms playing these games, in psychology, economics, and political science, studying how humans play these games under different conditions. And to my surprise, there was no work on having humans and machines play. And one of the reasons is because most reinforcement learning algorithms actually don't converge fast enough in these types of games. So I was very fortunate that one of my colleagues at the time, I was working in Abu Dhabi, about 10 years ago, and Jacob Crandall was an expert in reinforcement learning algorithms and has developed one of these algorithms called S++, which is a meta reinforcement learning. It's called an expert algorithm. So it's like a meta algorithm that controls multiple other algorithms, and it's designed to play generalized repeated games. And it has some properties. It's nice, lenient, and forgiving. And in simulation, when you pit it against all sorts of other reinforcement learning algorithms, you see here that S++, this is, I think, in self-play, the average payoff is that it actually converges way faster. you could see that if you could use deep Q learning or M cubed and model-based reinforcement learning, all these kind of standard algorithms, they take thousands of rounds to converge or sometimes never converge, which is a really big problem technically to be able to actually design algorithms that play with humans. So I'm going to skip the details of the algorithm. But this basically just to kind of give you a sense that it's an expert algorithm that has lots of experts. Each expert computes some strategy, and then there's a meta algorithm that selects one of those strategies, tries it out for a little bit, and then updates its aspiration levels. And then every model then updates itself, and then you start all over again. And in a sense, it doesn't matter that I don't fully understand this algorithm. In fact, I think Jacob is the only person who fully understands the algorithm. He wrote like a 50-page paper about it. And then there was another version of the algorithm, S#, which is based on S++, but with pre-programmed verbal responses. So it can send threats and promises and things like that. And this is a finite state machine description, basically of the process that generates these messages. For example, there are different states, like the partner profited from a defection or the partner defected, the expert forgives the other player and so on. And then based on which state you are, or what event happens in which state you are in, you could say, okay, I forgive you, or we're getting rich, or you betrayed me, and things like that. So what we did is we pitted this algorithm against, well, first of all, we have humans play Repeated Prisoner's Dilemma, Game of Chicken, and Alternator Game, which is a kind of coordination game. And people didn't know how many rounds were left. And as you can see here, when humans play these games, for example, let's focus on Prisoner's Dilemma at the bottom. People don't really cooperate much in the Prisoner's Dilemma. The baseline cooperation rates of mutual cooperation is low. With communication, it improves. Like when you allow people to send these kind of messages from like a menu, it improves. And now I want to show you here that human with S#, okay? So this, or S++. And you could see that the algorithm is achieving kind of comparable levels of cooperation with the humans, despite, and this is important, you see here at the beginning, in the Prisoner's Dilemma, there's much lower level of cooperation with the human. But eventually cooperation does emerge. And then this is self-play. So when the algorithm plays with itself, it does even better. And that's an interesting question in its own right. Like the AIs may not want to play with us anymore in the future. So let's look at so this is kind of a purely behavioral perspective using like a behavioral experiment like you would do to study human cooperation. And then we got people's subjective ratings. People find that the partner intelligent, has clear intent, and sends useful signals regardless of whether it's a human or an algorithm. But people were able to guess. So they were able to guess whether they were playing with an algorithm better than chance. So because people knew that they might be playing with an algorithm or with a human in this experiment, but they didn't know which one. And we asked them to guess. And it's interesting to look at the types of messages that the algorithm was using compared to humans. So even though they were both successful at cooperating, the algorithm was more threatening, like it was using more anger and more threats and less praise than the humans. And it was also issuing more planning actions, right? Like planning utterances, like, okay, let's do this. If you do next time, let's cooperate. Or if you do this, I'll do that. And it's just kind of interesting because, if you were comparing, let's say, two groups of humans, let's say, I don't know, teenagers with adults in playing this kind of game, that you would do exactly this type of behavioral experiment. And you might see something similar. And again, this is without knowing anything about how the algorithm actually works. Okay, so then we did a follow-up study, which explores the question of, should we reveal the bot's identity, right? So in the first experiment, people didn't know who they were playing with, but they knew that it could be a bot. So what we've done, we were motivated by this project called Google Duplex, which is an extremely realistic chatbot that or a voice chatbot that calls people or answers phone calls and takes, for example, restaurant reservations and so on. And when it came out, it was so realistic that it angered a lot of people. So the Washington Post was asking, should it be required to tell people that it's a machine? And then subsequently, Google actually announced that they will always reveal, the bot will always reveal its identity as a bot. So it will not trick people into thinking it's a machine. Obviously, it's just a matter of time before this becomes like very available, this type of technology. So I think this is a longer term problem. And it's already being deployed, by the way. It's calling businesses to check if they have like, toilet paper and things like that. Okay, so what we've done is to explore the question of, well, if a bot calls, if you call a customer service agent, let's say, and the agent tells you, okay, I'm a bot, and you're a very angry customer, will this interaction be as effective as it would be if you were talking with a human? Because with a machine, maybe we don't have to be as polite if we know that we're talking to a machine. So we wanted to explore this question, and this is a follow-up study led by my former student Fatima Ishowo-Oloko, and it's about efficiency, transparency trade-offs in human-machine cooperation. So what we've done is we repeated the experiments that you've seen before, and we varied what we told people. So sometimes they played with a bot, and we told them they played with a bot. Sometimes they played with a bot, and we told them they were playing with a human, and so on. And let's look at the results quickly. You can see over time, so this is what happens when they are playing with a human, okay? So a human is playing with another human, but if you tell them that it's a bot, the cooperation level is significantly lower, okay? So there is a kind of bias against bots, and we don't know yet what causes this bias. It could be because they think it's okay to exploit the bot. It could be because they think the bot will not be cooperative, will not be equally cooperative with them. It's not human after all, doesn't have emotions. And I think this remains an open question. Other people have also recently done some steps in this direction. But I think this is important to recognize, because if you think you're playing with a bot and then you actually lose out, like the human, him or herself are also losing out, because they're not cooperating. They're not benefiting from the mutual cooperation. So their payoffs are lower. So it's equivalent to calling the customer service agent, and when you know it's a bot, you start screaming, and then the phone call takes longer. Like your problem is actually not resolved because you did not subscribe to the usual norms of interaction. And what's interesting is that the best scenario was when you're playing with a bot and you thought it was a human. So the best scenario for human-machine cooperation in this particular game is when you deceive people. When they play with a bot that's very nice and cooperative, but they think they're playing with a human. We tried, by the way, a debiasing condition where we disclosed that it's a bot, but we suggested to people to treat it like a human, and that didn't make any difference. So it doesn't seem to be straightforward to get rid of this effect. Okay, so as you can see here, the worst case scenario is when you're playing with a human and you think it's a bot, right? Okay, so that was kind of, let's say, an adventure in human-machine cooperation, which is a study in a behavioral study of machines and how they interact with people. Now I would like to talk about human perception of machine behavior, and specifically the idea of cooperating through machines. So this ethical dilemma of autonomous vehicles that we've seen before, and the question of, not how the machine behaves, but what do people want the machines to do. Okay, so what we found, well, first of all, let me get the elephant in the room out of the way. Does it matter? This is never going to happen. These accidents are completely rare. And I could do something like this. I could say, look, here's an example accident in Michigan that, where a car had to swerve, to hit a pickup truck or whatever to avoid two people, right? But that would be dishonest because it's really not common, right? This type of explicit ethical dilemma. However, I want to convince you that a statistical version of this problem is extremely common. So think of this scenario. You have a bicycle lane on one side and you have a big truck on another side. And you're driving. And your question is very simple. Where should I put the car? In the lane. Should I go a little bit further from the truck to minimize the chance of hitting the truck? Or do I go a little bit further from the bicycle to minimize the chance of hitting the bike? And this is obviously in any given situation, this is not going to make any difference. But over millions or billions of instances of the situation, you may end up with different distributions of fatalities, right? So if the car is programmed to always be close to the truck and away from the bike, maybe the statistical probability, the probability of an accident, of a collision with the truck will increase versus, the other option, in which case you're probably more likely to sacrifice the cyclist, but save the passengers. So, and this will apply, this type of statistical distribution, statistical risk dilemma will apply to all sorts of things, like when do I take over? How much space do I leave in front of me versus behind me? If there's a motorbike behind me, do I leave more space? Do I brake slower if there's a car, and risk collision with the car in front of me, so that I don't, the motorbike behind me doesn't hit me, which is very bad for motorbikes. So I think we're going to face a lot of these questions soon. And this is actually, if you look at some of the early patents from the autonomous car development industry, this is a figure from the actual patent describing an autonomous car which is stuck behind a truck. The truck is stuck at the lights, and the car is trying to decide whether to overtake the truck. And this is a two-way street. And there's literally this table in the patent application, which shows the risk penalty based on the probability of different events and the magnitude of the risk. For example, there is a risk of getting hit by a large truck, and that's the risk magnitude. It's a very low probability event. There is a risk of getting hit from behind. There is loss of information as well, which is not very costly, but has high probability, and so on. So this type of basically decision theoretic reasoning about risk is very likely going to be taken, programmed, implemented in some way into the vehicles. And obviously it will entail different distribution of risks to road participants. So I think that's the problem, the true ethical dilemma of autonomous vehicles. Having said that, obviously we're using these kind of simple examples because when you run experiments with humans, you want to simplify away all of this uncertainty, right? Because you want to focus specifically on the trade-offs. So back to this, when we ask people here, what should the car do? The majority would say the car should save more lives. But then when you say, which car would you buy? You get a completely different answer. People say, I would never buy the self-sacrificing car, but I want everybody else to. And this is what we call the social dilemma of autonomous vehicles. This is work with Jean-Francois Bonafont and Azim Sharif. And the reason it's a social dilemma is because everybody knows what the right thing is. They know they want to live in a world where cars save the biggest number of lives, but they don't want to make their personal contribution to this outcome, right? So they have an incentive to deviate. It's a cooperation. It's like a prisoner's dilemma. But it's a multi-person prisoner's dilemma, which is called the social dilemma. When we ask people, what if we regulated all cars to save more lives? A lot of people said, well, then I would not buy an autonomous car. I would rather drive myself, which is a shame if the autonomous cars become safer. So there is a meta-ethical dilemma, which is if you force cars to be utilitarian to save more lives, you delay the adoption, right? And if you delay the adoption, you might cause more death along the way. So it's a non-trivial problem to solve. Okay. So one potential solution to this problem, and this is not my work, this is work from some people at Harvard University, the idea of the veil of ignorance, or a kind of social contract. And this idea goes all the way to another Harvard professor, John Rawls, who's an ethicist. He has a very famous book called The Theory of Justice. He came up with this notion of the veil of ignorance, which when you want to choose which society to be in, you choose without knowing who you are, right? So you don't know if you're going to be the sick person, the disabled person, or the healthy person, like the able person, let's say. You don't know if you're going to be a male or a female. You don't know if you're going to be, like born rich or born poor. And then you, behind this veil of ignorance, you're ignorant of who you're going to be. You choose what society you prefer. And according to John Rawls, then you choose the just society, right? The rational choice is to choose the just society. And so Karen Huang, Josh Green, and Max Bazerman at Harvard University wrote this paper using the veil of ignorance to see if it has impact on experimental subjects. And what they've done is they've asked people, you don't know if you're going to be a pedestrian or a passenger. How would you like the cars to be programmed? And in fact, and I try to explain it here in this cartoon. So here is John Rawls. This is like a game show, right? So John Rawls is asking you, once you've decided what the car should do, the wheel of fortune here decides who you will be, right? So you're looking at this dilemma. The dilemma is, the car should run over 3 pedestrians or hit a tree and kill the passenger. And obviously, and then you don't know who you're going to be, but there's a 1 in 4 chance that you will be a passenger and a 3 in 4 chance that you will be a pedestrian. So the rational thing to do is to say the car should sacrifice the passenger in this case. And that's exactly what they found. So in the study that I mentioned earlier, what they found is when you prime people with this idea that they could be anyone, then they're more likely to choose the utilitarian option and to opt into this kind of social contract. So there is some hope. Okay. Then in relation to this, we started a website called Moral Machine, which Miguel mentioned earlier, to collect more data and to do more variations on the dilemma. You can go visit the Moral Machine yourself. And it's basically asking people what the car should do. And here we vary all kinds of things. There's always 2 outcomes only. Here the car could go straight and hit these people, 3 people and a dog, or it can swerve and kill the person and hit the barrier and kill the person in the car. Notice that the people here are crossing illegally. It's a red light. And indeed, we vary. So we varied lots of factors like interventionism, like whether to swerve or not, the relationship to the autonomous vehicles, whether people are crossing legally or illegally, and then different types of characters. Because we wanted to understand whether people think the car should use these factors, like age, for example, to make decisions. And these are all the characters involved. Now, we were very lucky that the game got lots and lots of coverage from the media, which brought a lot of traffic to us. It also got a lot of coverage from YouTubers, which also brought in millions of people to the Moral Machine. And as a result, and at the same time, we translated the website to 10 languages, so we got millions of users. These are the numbers at the time of analysis. But actually, the numbers have more than doubled since, because we continue to collect data. And this is the global distribution of these data sets. And we published this work in 2018 together with Joe Henrich and Jonathan Schultz, who are kind of cultural anthropologists and economists who specialize in cross-cultural variation in moral behavior. So let me show you the results from the entire data set here. So we've done conjoint analysis, which allows you to estimate the effect of different factors in this type of binary choice experiments. So this is what happens. So what this shows is what's the probability of survival if you change the thing on the left with the thing on the right. So if you take a pet, a dog or a cat, and you replace the pet with a human, then there is a 60% increase in the probability of survival from whatever base rate is, right? So it shows here that human value is very important, and that's actually the most important factor. The second most important factor happens to be sparing more people, right? So more lives. So people have a very strong utilitarian intuition. And then these are all the other factors. And obviously they get kind of controversial in some cases but again, this is descriptive. This is just describing what people think the car should do, not what the government should allow, right? But some of them seem kind of sensible, sparing young lives, for example, sparing babies or older people. And that's a very strong effect as well. Sparing people who cross legally and sparing people of higher status, which is a little bit surprising. It has this almost the same strength. And there's a preference for sparing females over males, slight preference for sparing pedestrians, and so on. But these are a little bit smaller in relative terms. But what's most interesting, I think, is given the size of the experiment, that we were able to repeat this type of analysis at the level of countries. And then we're able to simply take, basically a vector of all the effects sizes of different countries, and then you have a distance. You can compute the distance between two countries, and you could run clustering algorithms. And when you run the clustering algorithms, and this is, remember, basically bottom up, you get interesting differences between countries that are very stark. So here's the global average on a radar plot of the different effects. You can see sparing humans is the biggest here. And this is, for example, Germany, where I'm now based. You can see the Germans have a greater preference for inaction, so to not intervene, to let the car go straight than the global average. They have a lower preference for higher status than the global average. And the rest is more or less the same or very close. And just for contrast, this is China, the Chinese sample. You can see that it varies substantially on some factors. For example, much lower. So the Chinese participants still prefer to spare young people, but just nowhere near the same strength, the same extent. And they're also not as utilitarian, right? Which is kind of understandable because utilitarian ethics kind of was formalized in the West. But and maybe surprisingly, that the sparing the lawful was even stronger than in Germany. Okay, and then when you do this on all countries, you get these kind of beautiful clusters. The colors here come from like hand-coded classification of countries from the field of cultural anthropology, but the structure that we have here is purely data-driven. And you can see there's an agreement, right? So there's like this kind of very big southern cluster, like South America, and you have a very big largely European cluster. And even within the cluster, you can see, for example, Commonwealth countries clustering together and things like that. And this is the Eastern cluster. And I refer you to the paper to learn a bit more about like how these clusters differ. But it raises some interesting questions. For example, an autonomous car built in the West may not have the same values, as some of the Eastern countries. For example, those Western driverless cars don't respect the elderly. And it raises a question also about localism in AI. For example, a car crossing the border from Italy to Switzerland, should it activate a different kind of mode, right? Like more rule abiding. And that's a question for regulators, obviously, not for us. But we've written a paper in Communications of the ACM in which we talk about the advantages and disadvantages of this type of crowdsourcing approach to studying AI ethics. And we think that this kind of data is only a small part of the bigger regulatory picture. That obviously you cannot just take these decisions and program them into cars. You have to take into account fundamental rights and things like that. So to summarize the talk, I spoke about 3 topics. The first topic is machine behavior, and here are the takeaways. So the first takeaway is that AI and machines in general can be the object of behavioral study in their own right, and collaboration across the behavioral sciences is something that's very valuable. It's something you already know. And I think computational social sciences are especially equipped to handle this type of challenge. And it's basically this paper is kind of an invitation to broaden the scope of study of machine behavior even further. Then I spoke about cooperating with machines, which is a study of one example of study of machine behavior. And I showed an experiment where we demonstrate that emergent human AI cooperation is feasible. And we showed trade-offs between transparency and efficiency about the nature of who you are interacting with, like whether you disclose that you're interacting with a bot or not. And finally, I spoke about human perception of machine behavior, and this specifically how we can cooperate about how to program an autonomous vehicle. And I showed that this can give rise to social dilemmas. And through the model machine experiment, I showed these interesting cultural differences in ethical values and expectations of AI. So if you're interested in learning more, here are the papers. And of course, I have to acknowledge all my co-authors without whom this work would never have happened. Thank you.
Unmute yourself, Miguel.
Sorry. Thanks a lot, Iyad, for the wonderful talk. I reminded everyone that you can use the Q&A panel for writing your questions. And well, just while people add questions, I had one question about. So I think it touches a bit the both. Both points that you were discussing about cooperation with and through machines. So I understand that well, part of the many of the experiments that you were talking about today were related. Have these prisoner dilemmas or like a cooperation through one-to-one interactions, because they are what we can control in a lab and where we can find reliable results. But also like what comes to mind when I think about cooperation with or through machines in our real lives many times is like a many-to-many interactions, or I don't know, for example, social media, where you have different layers with algorithms that sort content or organize how users interact with themselves. And I was wondering how that applies, or this kind of research could scale to this more massive and emergent setups where what the machine does influences of how people confront or collaborate, or so confront each other or collaborate to gather or verify information, or even how the economic interests enter the picture of how companies want to keep people engaged and so on. So how this research agenda can scale to more massive, emergent kind of setups, which I think is also one of the interests of many people in the alliance.
Absolutely. I think it's a great question, because it allows me to kind of acknowledge some of the work that's happening, elsewhere. And I think this is already happening in many ways, right? So if you think about, let's use an analogy. When you think about the study of animal behavior, you have in vivo and in vitro, right? You have and you have computational models. So you have people doing computational modeling of behavior, for example, and then putting like a mouse in a maze, right? Or putting like a little bacteria in some different, I don't know, salinity condition or temperature conditions, and observing its behavior, which gives you kind of very high control, but less ecological validity, right? You don't know if this behavior generalizes beyond the lab, but you start there. And then you have like, in the wild, people like Ian Cousin, who was one of our co-authors on the paper, like putting devices on, like he would do everything, right? Like he would do computational modeling of, let's say, swarm behavior or fish school behavior. And then he would actually get like an individual fish and put it in a virtual reality environment. Like that's a very kind of, that's very specific. And then you have, birds or fish with GPS on them being observed. And I think we're doing something similar, or we could do something similar. We're already doing something similar with machines. You could study them in the lab. You could have a model, you could study them in the lab, like what we did, and then you could study in the wild. But obviously, the more real world you get, the harder it gets to do experimental controls. So, and for a variety of reasons, you don't have no control over the algorithm that Facebook is using to rank news. You don't, and if they change the algorithm, it's, how will you even know? So there's lots of like ecological validity kind of questions that arise there. So you have a trade-off between control and often, which is often why a lot of people do just purely observational studies with these type of systems. Like, okay, let's observe what people do. Let's observe the behavior of bots, people like Emilio Ferrara, for example, and quantify the behavior of bots online. But there are people who are doing more experimental work. For example, Chris Bale is a political scientist at Duke, who's doing, he would expose some people to certain bots and other people to different bots or no bots, and then sees if there's a difference in the outcome. Kind of from the outside, because he can't collaborate with, I think he doesn't have a collaboration with Twitter, so he's unable to, and Twitter makes money out of this, right? So it's very hard for them to allow somebody to fiddle with their algorithm for non-commercial purposes, right? So I think there's a kind of trade-off here as well that we have to deal with. But I agree with you. I think we need to study this at all scales, as well as different environments. But we need to be aware of this trade-off between control, experimental control, and external validity. Yeah, I think there's a couple of questions.
Okay, yeah, thanks a lot. Yeah, so there is a question from Stavros Anagnou. So he has seen, is there any examples or scope into AI agents adapting to cultural context, and which mechanisms could serve this purpose?
Oh, that's a fascinating question. I don't know yet. I mean, I think it's hard to know, right? I mean, there are, we can't call them AI agents, but like in information technology in general, like social media, like different countries have different censorship laws, right? So perhaps this is one example where this kind of cultural, let's say, call it sovereign legal expectations can shape the behavior of the algorithm. Like what counts as like misinformation or let's say, hate speech in one country may be different from another country. And I think that's already something, the algorithm itself is not learning on its own how to do this. I think the programmers are learning, through interaction with the government or with the users. But that's kind of one maybe early example. But I think as we automate things more and more, these things are likely to become more automatic. But I can imagine, but a simple one is just, bots using different language, right? Like what does, like these things like Alexa and Siri, when they speak French, like how is it different from when they speak English? Like, is it only the language difference, or is there something else fundamentally different because of the language model underlying it, right? Because of the way that the French describe the world is a little bit different from non-French people. So I think it's already happening in some cases, but I think it would be a bigger, like especially when the stakes get higher, and when you're dealing with trade-offs, like what is okay for children to be exposed to, for example, across cultures and so on. What do conservative cultures want? Do they want the toys of their children to behave a little bit differently, right? I imagine this will become an issue fairly soon.
Okay, so Michael Hayder is asking, when analyzing what humans thought how driverless cars should react, did these findings differ from what we expect from a real driver to do, and if do we or should we hold an artificial intelligence to a different standard than a biological human or intelligence?
Yeah, so difficult question again. So humans obviously are very bad at doing something like this, right? So basically, if you think about what we've done so far, if you all of a sudden, like a child runs in front of the car and you don't have the technology to stop, right? The car cannot stop itself, which now a lot of cars can actually do this on their own. But let's say before this, you hit the child. It's a tragedy, right? But then you can't do, for example, criminal prosecution because you say, well, there's no way this person could have known, so maybe there's some kind of other civil liability or something like this. And again, I'm not like a legal expert, but I think we take human limitation into account when we evaluate this scenario. The other important thing is, this is Jonathan Zittrain, Harvard, who teaches tort law at Harvard. I asked him, like, what happens today, like if you do make these decisions? And he said, today in the legal system in the US, no matter what you do, you're okay, because if you decide to swerve, that there's a reasonable defense of that decision, and if you decide to stay, there's also a reasonable defense of this decision because it's just a very difficult decision. But if you program the car 6 months before to make a certain decision in that scenario, that's a different kind of scenario, they have the ability to make a more informed choice. And there also it becomes a more deliberate choice, right? Because you're programming a behavior into the vehicle explicitly. And that's again a difficult question, like has it been programmed explicitly or did it learn it on its own through the simulations that they were run and so on. So I think we have lots of questions, open questions about that then determine whether it's fundamentally different. But I do think that the cars should be held to a higher standard because they have higher capability in this particular case, right? So we need to expect more from them than just to say, just imitate the human. That would not be a good strategy because the humans are not very good at this.
Okay, great. So Young Kim is adding to these questions. So asking if we should hold people from different backgrounds to different standards, and raises the concern that if this will allow or result in the formation of moral bubbles where different standards apply depend on people's consideration.
Yeah, we already live in moral bubbles, right? Like we have different countries, different cultures. I mean, cultural diversity is all about moral bubbles. Different cultures have different moral standards. And it's, some people think that's a good thing, and some people don't think it's a good thing. So I think it's a very broad, it's a very fundamental question about the nature of society and what it is to be human. But but to make it a little bit less extreme, we have both. There is room for both. So if you think of traffic law today, we have universal traffic lights. Red means go stop everywhere in the world. The stop sign is the same everywhere in the world, which makes it easy for us to move around, right? To drive from one country to another. But you have local rules, like, in Australia, where I did my PhD, you drive on the other side of the road. The driver steering wheel is on the right. And you have different regulations for speed limits and for who takes priority at an intersection. So I think there is room for both, and maybe, but to do this, you need like international standards, and you need kind of negotiation and through these international bodies, while also respecting local rules and customs.
Okay, great. So perhaps we have a time for a last question. So Olaf will toss this. Okay, thanking you for a great talk. And so asking about cooperation, you talk about cooperation with and through machines, but what is your vision in terms of the rights of the machines themselves, or perhaps hybrids too? Also, what's your vision about these rights of the machines in future, and what are the steps we should take in this perspective?
Great question, also difficult question. And I must say that I'm not an expert in this area. Like I mean, whatever I say is like a kind of a personal guess. Because it's really hard to think about the future, like this far into the future. I think in the short term, there's nothing like this. Maybe you could have, some people are talking about legal personhood for machines. So in the same way that the corporation is a legal person, which means that you can sue the corporation, or the corporation can own things and can enter contracts. So some people are saying that doing this for machines, for AI systems might enable, might improve things, might be helpful. But in terms of machines having rights, like for example, not to be switched off, I really don't know. Enough to answer this. I think if at some point machines become so sentient and conscious, I think honestly, this is the last, this is not the biggest question on our mind at that time, right? Like it's probably going to be an existential question about, will we even be around? Or perhaps, we will be hybrids and completely morphed. So I don't think there's anything fundamentally stopping that, but I think by that time, so much else will have changed that the question may be completely different, the nature of the question. But thank you. It's a nice way to finish up.
Okay, great. So I think time is over now. We have now there is the ISOL Award session. So thanks a lot, Iyad, for the wonderful talk and discussions. And just want to remind everyone that we have a Keynote channel in Slack. So if anyone wants to continue the discussion there, it's open. Thanks.
I would like to say also thank you for your talk. And now we will have the session with the ISA awards, and I suggest to make like 10 minutes break before it, not because in the schedule there are 2 hours for it. So I think